In this example, we're going to talk about gravitational potential energy. And a boy has a book with a mass of 2.8 kilograms, and he's lifting it from a desk up to a shelf. And we're asked to solve for the potential energy of the book on the shelf relative to the floor and then relative to the desk. Remember that potential energy is always relative from some location. We generally say that it's relative to the ground. So if it's not saying something specific, it means relative to the ground. But it is relative to something in all cases. Our book has a mass of 2.8 kilograms. And the desk is 0.75 meters high. And the shelf is 2.5 meters high. So if we calculate relative to floor, our potential energy is equal to mg height from the floor. So our PE is equal to 2.8 kilograms times 9.8 meters per second squared times 2.15 meters. And when we do these calculations, we get that the potential energy, rounded to two significant figures, is 59 kilogram times meters squared per second squared, which we just said was a joule. If we want to talk about relative to the desk, then it's the same equation. We just have to use the height from the desk. So it's the same mass. It's still on the same planet, so the acceleration due to gravity is the same. And now we want to know how much higher than the desk. And in this case, it's 1.4 meters above the desk. Relative to the desk, our potential energy is 38 joules. This problem can be solved in another way, at least parts of this problem, because you could calculate how high he moved it and the force he used, which would just be the weight, this times 9.8, and we could calculate the distance, force times distance, to get the amount of work done to calculate the change in potential energy. So particularly once we get to energy and conservation of energy and work energy theorem, there are multiple ways. As long as your logic is sound, it's fine.